Welcome to the deep dive. Today, we're really getting into the nitty-gritty of machine learning.
hmm Specifically, supervised learning.
Right, using labeled examples to make predictions. And our sort of mission for this dive,
Yeah, it's to get a really clear handle on regression.
regression. That's predicting continuous stuff like numbers, right? Not categories.
Exactly. And also, how do we figure out if our predictions are actually, any good? We're leaning on some lecture material from applied data science here.
Okay, sounds good. So, regression first, predicting values.
Yeah, they're predicting sales figures based on different inputs. It's different from classification, which would be like, is this email spam or not spam? That's a category.
Got it. So the source material has this example, right?
Yeah.
Advertising and sales.
Oh, yeah, it's a great one. Data from, I think, 200 different markets.
Yeah, showing how much they spent on TV, radio, newspaper ads.
And what the sales were afterwards.
So the key questions are, well, first, is there even a link between the ad money and the sales?
And critically, if there is, can we actually predict future sales if we know the ad budgets?
Makes total sense. So how do we approach that mathematically?
Well, that's where linear regression comes in. We basically try to draw a line, or a plane in higher dimensions, through the data points.
Okay.
The idea is to model the relationship. We write it as an equation. Y books plus B or X and so on.
Where Y is sales and the X's are the spending on TV, radio, newspaper.
Exactly. And those beta symbols, those are the numbers we need to figure out to learn from the data.
Learn them. How? What makes one set of desks better than another?
Good question. We want the best that make our line fit the existing data best. The lecture calls this minimizing the empirical risk.
Empirical risk. Sounds fancy.
It just means minimizing the errors on the data we have. Specifically, we look at the difference between what our line predicts for sales and what the actual sales were for each market.
Okay.
Then you square those differences.
I square them.
Well, partly so. Positive and negative errors don't cancel out. And it also penalizes bigger errors more. Then you add all those square differences up.
Right.
And we want the values that make that total sum as small as possible.
So finding the best fit line by minimizing those squared errors, is there like a direct way to find those best?
Yep. There's actually a formula for it in linear regression. It involves some matrix math. The little hat on the IO just means it's our estimate.
Okay, don't need to dig into the matrix math right now, but basically we plug our data in and it spits out the best bat value.
Precisely. It finds the coefficients that minimize those sum squared errors.
So for the advertising example, what did the results look like? What were the bat values?
Okay, so the source gave this result. Sales, 82.94 plus 0.046 times TV spending, plus 0.1 times radio spending, plus 0.001 times newspaper spending.
Interesting numbers. The 0.19 for radio seems much bigger than for TV or newspaper.
It is. And that's the interpretation, right? For every extra dollar or unit spent on radio ads, sales go up by 0.19 units, assuming TV and newspaper spending stay the same.
Holding other things constant, yeah. So TV ads 0.046 per unit and newspaper only 0.001. That seems tiny.
It is very small in this combined model. And interestingly, the source also showed a simpler model just using newspaper.
Oh, what did that look like?
That was sales equals 0.35 plus 0.055 times newspaper spending.
Wait, so in that one, newspaper has a bigger coefficient, 0.055, than it did in the combined model?
Exactly. And this is super important. The effect of one variable can look different when you count for others. Maybe newspaper spending is correlated with TV and radio, and they were capturing most of its effect in the big model.
Huh, okay. And what about the 2.94 at the start of the big equation?
That's the intercept. That it's the predicted sales if you spent absolutely zero on all three types of advertising. Your baseline sales.
Right, makes sense. Okay, so we have this model, these coefficients, but how much faith should we put in it? How well does it actually predict sales overall?
Excellent question. That brings us to performance assessment. And a really common metric for regression is R squared, written R Berman.
R squared, heard of it. What does it actually tell us?
Think about all the variation in sales across those 200 markets. Some sold a lot, some sold less. That's the total variation, sometimes called TSS, total sum of squares.
Okay, the total spread in the sales data.
Exactly. Now, our regression model tries to explain why some markets sold more than others based on ad spending. But it won't be perfect. There will still be some variation it doesn't explain. That's the leftover variation, the errors, called RSS, residual sum of squares.
Got it. Total variation and the leftover variation after our model does its thing.
Right. R squared is basically tells you what fraction of that total variation your model did manage to explain. The formula is R REIUP equals 1 RSS TSS.
Ah, okay. So 1 minus the fraction of variation that's left over. So a higher R squared means less leftover variation, meaning the model explained more.
You got it. R squared is between 0 and 1. 0 means the model explains nothing. 1 means it explains everything perfectly, which rarely happens with real data. Higher is generally better.
So what were the R squared values for the advertising models?
Okay, so for the model with only newspaper spending, the R squared was really low, only 0.05.
Wow. So newspaper ads alone explain only 5% of the variation in sales.
Pretty weak, yeah. But when they used all three, TV, radio, and newspaper, the R squared jumped way up to 0.897.
0.897. So that combined model explains almost 90% of the sales variation.
Yeah, much, much better. TV alone was around 0.61, radio alone 0.33. So combining them gives a much fuller picture.
That really shows the power of looking at multiple factors together.
Definitely. Though, one quick caveat, just adding any variable tends to increase R squared slightly, even if the variable isn't truly helpful. It can never go down when you add a variable.
Oh, okay. So a high R squared isn't the only thing to look at.
Right. That's why people sometimes use adjusted R squared, which tries to correct for the number of variables you've thrown in. But for a basic understanding, R squared gives you a good first measure of fit.
Okay, this is starting to form a clear picture. Regression lets us model these relationships, estimate the impact of different inputs,
Like ad spending on sales.
and R squared gives us a score for how well that model captures the real-world variation.
Exactly. It's about quantifying relationships and assessing prediction quality. The advertising example is great because it shows different factors contributing and how the combined view is often much more insightful.
But even that combined model, with an R squared of almost 0.9, it still leaves about 10% of the sales variation unexplained, right?
That's right. No model is perfect. There's always noise or factors you haven't measured.
Which leads to a really interesting final thought for you listening. If nearly 10% of sales variation isn't explained by TV, radio, or newspaper spending in that data, what else could be going on? What other factors might be driving sales in those markets? Something to chew on.
Yeah, definitely food for thought.